Hi, welcome back. Today we will be solving Physics Standard Level Paper 1. It's November 2016 paper, time zone 0, and it will be 45-minute MCQs questions. Okay, let's start. So question number 1. Is a boy jumps from a wall 3 meter high. What is an estimate of the change in momentum? So we need to find change in momentum, so let's call it delta P. And we are given the height h. So there's a boy, so he must have some mass which is unknown, and since it's a problem estimation, we have to just approximate the result when he lands without rebounding, so there's no rebound. Okay, let's see what is the situation here. The situation here is that there is a boy here and he has some mass which is unknown, and this is the ground, and we have a height of h, and this h is 3 meter. Okay, so on this boy there's a weight for this boy, and that weight is given by mg. Okay, change in momentum. So the equation for momentum as given in the data booklet is momentum equals to mass times velocity. So momentum is a vector quantity, so it is direction dependent, velocity as well. So this is the equation that we will be using. Now in order to find change in momentum is given by mass times change in velocity. Now the reason why this equation is true because the mass doesn't change, and any change in velocity will lead to a change in momentum. Now let's open up this equation more clearly. So in order to find change in velocity is just final velocity minus initial velocity. So when the boy starts from here, he has some initial velocity, call it 0 because it starts from rest, and when it lands here it has some final velocity which we don't know. Okay, now in other words, you can see since the initial velocity is 0, this thing just becomes 0, so it will be just v minus 0, just v. So the change in momentum is just mass times final velocity. Now we need to come up with the solution to find this final velocity. So in order to find final velocity, we will use conservation of energy. Conservation of energy, call it CE. So according to the conservation of energy, the boy at this height, he has some potential energy. He has some potential energy here, and during its fall, all of that potential energy is converted into kinetic energy. So all of that potential energy is converted into kinetic energy as the boy descends. So we can write an equation. We will say, the entire PE, which is the gravitational potential energy, is converted into kinetic energy. And the equation for gravitational potential energy as given in the data booklet is mgh. And for the kinetic energy is half mv squared. Now just using simple mathematics, we can cancel the two mass, and we will try to make v the subject, so 2 will go up there, so it becomes 2gh, but you see there is a square here. In order to get rid of this square, we have to take square root on both sides. Here we have an equation for the velocity, so we have this equation. Now we will sub this velocity equation into this velocity. So after subbing this velocity into here, we will get square root 2gh. So this is our general equation for change in momentum. Now it's time to sub in all the variables and numbers into it. So the mass of the boy is not given to us. Since it's a problem of estimation, we have to choose a suitable estimation for the mass. So my mass will be around 65 kg. The 65 is not a good number to do manual calculations. Why not we just choose 50? So just use a reasonable approximation, so that it's easy to do manual calculation. So square root of 2g. G is the gravitational field strength, which is normally 9.81, but for easy calculation purposes, we will just choose 10. So we will round up. And times the height. The height is given to us, which is just 3. So let's use the mathematics. So it's 50 times square root of 10 times 3. 30 times 2 is just 60. So we have 50 square root of 60. Now we have to see what is the square root of 60. Well, in order to find square root of 60, since calculators are not allowed, what we will do, we will see, okay, if 7 squared gives us 49, 8 squared gives us 64, so 64 is the closest number to 60. So the square root of 60 will be definitely smaller than 7, so it will be like 7.5 or 7.6, something like that. So we can always round up to 8. So this thing will be approximately 8. So now we have 50 times 8, which is around 400. So any answer that says 400? No, but is there any option that is closest to 400? Yeah, part C. Question number 2. Light of wavelength 400 nanometer. So we have the wavelength 400 nanometer. So nano is 10 to the power of 9, negative 9. So we have 400 nanometer. Is incident on 2 slit separated by 1000 micrometers. So we have the slit separation, 1000 micrometer. The interference pattern from the slit is observed from a satellite orbiting 0.4 megameter. So we have the capital D, the distance between the screen and the slit, which is 0.4 megameter above the Earth. The distance between the interference maxima as detected at the satellite is, so we need to find S. The distance between the interference maxima. So actually we need to find 2S. Let me explain what this 2S is here. So what is going on here is, so imagine if you have a slit. So this is a slit, this is the screen, and this is just an imaginary baseline. This is capital D, and this much distance is small d, and you have the wavelength coming in this direction. So the wavelength is lambda. So here diffraction happens, and after diffraction you have these fringes. So the middle one, the middle fringe is always maxima. So after maxima you have minimum. So minimum is where destructive interference happens, and then you again have these maxima. So maxima, minima, they always occur in alternating order, starting always from the maxima. So we can also draw this right angle triangle here. This distance is S. Always remember, this distance is S. And the distance between the central maxima, from this maxima to this maxima, right, these two maxima is always 2S. So what is he asking us? The distance between interference maxima. So these ones. Not the middle one, because the middle one is always maxima, so there's no point talking about it because it's always going to stay there. So when we say central maxima, it is always N1 maxima, these two. Yeah, okay, so we need to find this 2S. Now the equation that we will borrow from our data booklet is going to be this one. So it's given in section 4.4, S equals to lambda capital D over small d. So let's make use of this equation. So S equals to lambda capital D over small d. Okay, now we need to just sub in all the values into here. So let's just try to erase this thing. Oh, let's just keep it here maybe. Okay, so we have S equals to lambda. So lambda is 400 nano. Nano is 10 to the power negative 9. And then we have capital D. So capital D is 0.4 to the power mega. Mega is to the power of 6. Divided by, so let's just keep it there. Okay. This thing is separate. Divided by small d. So small d is 1000 micro. Micro is 10 to the power negative 6. So let's try to simplify this equation. So what we have is these two 0 cancels out with these two, and we can give 1 0 to 0.4, so it actually becomes 4 times 4 times 10 to the power negative 9. So here we will have 5, so plus 5, use the indices so that power can be added up together as long as the bases are the same. And then we on the denominator we have 10 times 10 to the power negative 6 is negative 5, so negative 5 when it goes up becomes positive 5. So 4 times 4 is just 16 times 10 to the power of 1, so this is going to be 160 meter. Since we don't have any 160 meter here, but equivalently we can convert meter to kilometer. So 160 meter will be just 0.16 kilometer. Just divide this answer by 1000 to convert meter to kilometer. So it's going to be 0.16 kilometer, and then we have our option B. Yeah. Question number 3. A car moves north. So let's just draw the quadrant. First of all, to have an idea what's going on here. North, east, west, south, NEWS. Okay. So there's a car here, and the car moves due north. So the speed is 3 meters per second for 20 seconds. So it moves at a constant speed, and then it turns due east. So east and north, and then it travels at 4 meters per second for 20 seconds. Okay, what is the average speed? So we have speed, and we need to find the average speed. So the average speed, the formula is average speed is equals to total distance over total time. So when we say distance, we shall write total time over time. Time is also total. So average speed equals to, so let me write in a full form to make it more clear. Total distance over total time. Yeah. Average speed is total distance over total time. So the total distance traveled is this distance and this distance. So let's try to find both distance. So we know the speed equals to distance over time. Distance is speed multiplied by time. So we have two cases here. The first case is traveling in the direction of north at the speed of 3 and the time is 20. So the distance traveled in the north direction will be 60 meters. So for the second case, if still the distance is 4 is the velocity due east direction, and for the same time it's going to be 80 meters. So now we have to just add them together. So if we add them together, we will get 80 plus 140 meters. So 140 meters is the total distance traveled. So we can sub that 140 meters over here, and the total time traveled is 20 plus 20. So it was traveling at the total time for 20 seconds. So 20 in the direction of north and 20 in the direction of east. Let's simplify the equation. So we will have, let's simplify with the table of 2. So 2 is 4, 2 is 7, 7 divided by 2 is 3.5 meters per second. So there we have 3.5 meters per second. Question number 4. So in question number 4, we have an object of weight W is falling vertically at a constant speed in a fluid. So we have an object, and that object has a weight. The weight is W, so it's falling in a fluid. So when it's falling in a fluid, there's a drag that is opposing the direction of the motion. Call it D, drag. Now, as long as the speed is constant, there must be no net force acting on the body. So the net force acting on the body must be 0. So we already know the formula that F net, the net force acting on the body is equals to ma. This is the general formula. Always remember this force is net. Net means the pure resultant amount of force. So after cancelling all the forces, what is the force left behind? So you have this drag that is opposing the weight. Now a constant speed means there must be no acceleration. So this a must be 0. There must be no change in speed. Now for a to be 0, this net force must be 0 because mass can never be 0. Now this net force is 0 at the constant speed, and the only condition it will be 0 is when the weight becomes equals to the drag. So the drag starts to increase as the speed of the body increases during the fall, and a time comes when the drag becomes equals to the weight. So drag keeps on increasing, and the time comes when the drag becomes equals to the weight. That is the time when the net force becomes 0 and acceleration becomes 0. Hence, it travels with the constant speed. Yeah, it's very similar to terminal velocity case. What is the magnitude of the drag force? So the drag must be equals to the weight when the constant speed is reached. Yeah. Question number 5. An object initially at rest is accelerated by a constant force. So again we use this formula, so F equals to ma. So there's a constant force acting on the body. It means if this exists, then acceleration will also exist. So there is an acceleration and the body is like continuously speeding up. Which graph best shows the variation with time t of the kinetic energy and the variation with time t of the speed of the object? Okay, let's talk about the speed graph, speed versus time graph first. Now, you guys should always know that if you have a graph of displacement versus time, velocity versus time, or acceleration versus time, in order to go from a graph of displacement versus time to a velocity time graph, and from velocity time graph to acceleration time graph, you also need to find the slope of the graph. So going forward is like differentiation, finding the slope of the graph. And the reverse process will be finding the area under the graph. So in mathematics, you guys should remember it's integration. So we integrate, or in other words, in physics we say we find the area under the graph in order to reverse the direction. So for example, if you have a graph of acceleration time graph and you want to find velocity, you just need to find the area below the graph. Okay, so right now, all of these are velocity time graph whose slope gives us acceleration. Acceleration is a vector quantity. Force is also a vector quantity. So let's just draw an arrow above it. So we know that constant force exists. If there is a constant force, this constant force will lead to constant acceleration. If the acceleration is constant, it means the slope of this graph must also be constant, because the slope represents acceleration and acceleration is constant because the force provided is constant. Alright, so we just need to look for a graph with a constant slope. So this one has a constant slope, this one has an increasing slope, so don't choose this one. And this one also has a constant slope, this one does not have a constant slope. So we are only left with option A and C to choose from. You can just clearly reject B and D. So now we have less options to choose from. So this is a kind of a paper technique, so always try to cancel the options that doesn't make sense at all, so that we are left with less options to choose from. So it actually makes the problem more effective to solve. Okay, kinetic energy. So we know the formula for kinetic energy from the data book, that is half mv squared. Now, from the previous graph, we know that the velocity is just increasing. So if this velocity is increasing, then the kinetic energy will also increase because they are directly proportional. In other words, kinetic energy is directly proportional to square of velocity. You can see there's a square here, whereas this section is just constant. So this constant just disappears within this proportionality sign. So kinetic energy is directly proportional to square of velocity. So a graph of square, or like x squared, looks something like this. So for mathematics, it looks like a parabola, quadratic equation, right? Quadratic graph. So it has to be the one with the quadratic shape, so it's A. So you can see the kinetic energy is actually increasing proportional to V squared. Quadratic graph. So it has to be A. Okay. Two stationary objects of mass 1 kg and 2 kg are connected by a thread and suspended from the spring. Okay, so we have a spring here, we have 2 kg, and we have 1 kg here. The thread is cut. Immediately after the cut, what are the magnitudes of the accelerations of the objects in terms of the acceleration due to gravity g? Okay. Now let's talk about this 2 kg mass. So there's a weight acting on this 2 kg mass downward, and the weight acting on this 2 kg mat is weight. So actually what he's asking us for is to find acceleration due to gravity. Now if you So there's a weight acting on this 2 kg mass, okay, and there is a weight which usually is 1 kg mass also, and then the spring provides an upward force. Now the spring is responsible to withstand the load of both of these balls, 1 kg and 2 kg. So a total of 3g of force is exerted by this spring in the upward directions. So as we know, so weight equals to mg. So for the first one, we just need to replace the mass, this mass, by either 1 kg or 2 kg to find the corresponding weight in terms of gravity. So for the first one, for this one, it will be just 1g. So so weight equals to mg. So we just need to replace the mass by either 1 or 2, and then keep the g as it is. Don't put 9.81 or 10 into there. And for this one, it will be weight equals to mg. Just keep the g as it is and replace the mass by 2. So it will be 2g. Okay, so there's a total downward force of 1g plus 2g, which is 3g. So a total of 3g acting downward. And because everything is stationary, and because of which the spring must also provide an upward equal force of 3g in order to balance everything out and to make sure that the system is under stationary. The system is stationary. Okay, now when you cut the spring, this 2 kg mass falls freely under the influence of gravity, and the gravity being g. So after cutting down the thread, this 2 kg mass falls freely under the influence of gravity. Irrespective of the mass, the gravitational field strength acting on this 2g will still be g. So it doesn't matter how big or small this mass is, as long as it's falling freely under the influence of gravity, its acceleration will be just a g. So it's either this option or this option. So it's independent of the mass. Whereas for this 1 kg, this 1 kg doesn't fall freely under the influence of gravity because there is a spring attached to it. The spring provides an upward force of 3g, whereas the weight of the ball provides a downward force of 1g. So in other words, there is a 3g force acting in the upward direction and 1g force acting in the downward direction, which is due to the weight for this object, and the resultant net acceleration acting on this ball will be 3 minus 1, which is 2g in the upward direction. So we have to find the net. Net is the difference between the forces. Yeah, considering their vectors also, so the directions they are direction dependent. So it will be 3g minus 1g, which is just 2g. So it has to be the acceleration on 1 kg. 2g. Okay, question number 7. So a student of weight 600 Newton climbs a vertical ladder, 600 meter tall in the time of 8 seconds. What is the power developed by the student against gravity? So the equation for power is equals to energy over time. Now this energy can be any type of energy. It can take any form. It can take kinetic, or gravitational, or heat, or thermal, but in our case it has to be gravity because the student is doing work against gravity. So it will be potential energy, work done against gravity, which is gravitational potential energy divided by time. And the formula for PE, gravitational potential energy, is just mgh divided by time. Okay, now we also know that the weight is equals to mg, so why don't we replace this mg by w, which is the weight. So our new equation will be wh over t. Now I think we are good to sub in all the values into it. Now the weight is actually 600 times the height. So the height, the vertical height climbed is 6 meters divided by the time. So the time taken is 8 seconds. Alright, let's simplify. Let's take a table of 2. So 2 4s are 8, 2 300, 2 2s are 4, 2 3, and 2 1, 2 150. 150 times 3, so it will be 0, 450 watts. It's going to be 450 watts of power developed as the person does work against the gravity. A ball of mass m strikes a vertical wall with a speed v at an angle of theta to the wall. The ball rebounds at the same speed and angle. What is the change in the magnitude of momentum? So change magnitude of momentum. So in other words, it's just asking us to find the change in momentum, and we're only interested in the magnitude, not the direction. So the direction doesn't matter. So we are taking the absolute value of the change in momentum. So if the change in momentum is negative, we will just convert it into positive. So it's just interested in the magnitude of the ball. Okay. Now we already know that the equation for momentum is mass times velocity. So this is vector and this one is also vector. Now change in momentum will be equal to mass times change in velocity, because the mass doesn't change, mass stays constant. Okay. Now further on, change in momentum is mass times change in velocity is due to final velocity minus initial velocity. Yeah, we have to take the difference between the two velocities, final and initial. Okay, so in our case, as you can see, the velocity is at a certain angle. So what we have to do, first of all, we have to resolve the two velocity, the resultant velocity, into two components, horizontal component and vertical component. So I'm going to draw this new triangle section here. So there's a velocity here. So this velocity, so we can draw this right angle triangle. So this is the resultant velocity, and there's an angle here. So what we will do is we will apply SOHCAHTOA to resolve this resultant velocity into two components, vertical component and horizontal component. So just apply SOHCAHTOA rule. So if you don't remember the SOHCAHTOA, so for a right angle triangle, sine theta is opposite over hypotenuse, and cos theta is adjacent over hypotenuse. So this is some simple standard math level. So we always apply these. We also use the tan one, but there's no need to use the tan one here. So all these SOHCAHTOA is applied on the right angle triangle. So if you observe, so this is hypotenuse opposite. So this one will be v sine theta. So hypotenuse opposite. So opposite over hypotenuse we will use sine, and hypotenuse opposite adjacent. So adjacent over hypotenuse will be the cosine. Yeah. So we have our two component. So the horizontal component is given by v cos theta, whereas the vertical component is given by v sine theta. Now we will do the same thing for the same mass after its rebound. So it will have a horizontal component and it will also have a vertical component. So we will resolve in the same way. So after resolving it, we will get the same result. So it's v sine theta and v cos theta. Okay, so we have these two components again. Okay. Alright. Now, since momentum is also a vector quantity, so a vector quantity is direction dependent. So in our case, our change in momentum will be as a result of change in momentum in the horizontal direction, because there is a horizontal momentum because of horizontal velocities, plus any change in momentum in the vertical direction. So we have two components of momentum also, horizontal component of momentum and vertical component of momentum. All this is happening because the velocity is at an inclined angle, so we can always resolve resultant momentum into two components, horizontal and vertical components. So the total change in momentum will be due to any change in momentum along horizontal direction, and any change in momentum along vertical direction. Okay. Now, if you observe the vertical momentum, so in order to find momentum, we know it's mass times velocity. So why don't we just multiply all velocities components by the mass so that we get momentum. So here we have all the momentum. So we have horizontal momentums and vertical momentums. You just need to multiply this velocity component by the mass. Okay. Now if you observe vertical component of the momentum, so it's downward, right? Now, okay, so what's going to happen here is, so first of all, draw a box. Draw an imaginary box. Okay. Now, when this ball hits the wall exerts a reaction, normal reaction force to the ball. So this is the normal reaction force. This is as a result of Newton's third law. For every action, there is equal and opposite reaction from the wall. So the wall provides an impulse, an impulsive force to the ball, and this impulsive force is always perpendicular to the plane. So this is a plane, the wall plane, and the normal contact force is always perpendicular to the wall. So it has to be horizontal for it to be perpendicular to the wall. It cannot be vertical. Now, if you scan the boundary of this system, you will see, do you find any external resistive force acting on the system? You see here, yeah, this one. So this is coming from an external source. So it's an external force. And this external force is in the horizontal direction. So according to the conservation of momentum, so conservation of momentum says that for the momentum of the body to be conserved, to stay the same, there must be no external force acting on the system. So you can see, if you scan the boundary of this system, you will find that there are no vertical external forces acting on the system. If there are no vertical external forces acting on the system, then the vertical momentum or the vertical component of the momentum should stay conserved. It should not change. There must be no change in the vertical component of the momentum, because the vertical momentum is conserved, because there is no vertical external force acting on the system. So there will be no change along the vertical component of the momentum because it is conserved. And the reason why it is conserved, because there are no external vertical forces acting on the system, but there is external horizontal resistive force acting on the system, and it is external. So because there is a horizontal external force acting on the system, the horizontal component of the momentum will not be conserved, because we cannot no longer apply conservation of momentum along the horizontal direction. So the only change in momentum is due to horizontal component of the momentum. Okay, so again back to the same equation. So we know that the change in momentum is mass times final velocity minus initial velocity. So we have mass times final velocity is this one. So it's mv cos theta. But because it's moving in the opposite direction, we have to put a negative sign here, because velocities are direction dependent, so as momentum. So anything that is moving in the opposite direction should be given a negative sign, whereas anything moving in the forward direction, just give it a positive sign. So we have to be careful with this direction. So it's a negative, minus initial velocity is positive mv cos theta. So just simplify the equation. So minus minus, we just add them together. So we have minus, there's a 2 because they both are same, v cos theta. Now this is our change in momentum. Final. Now, since we are only interested in the magnitude, we will just take the modulus or the absolute value. So we will ignore the negative sign. Cos theta. So there we have our result. So section option B. Question number 9. Two objects M1 and M2 approach each other along a straight line with speed v1 and v2 as shown. The object collide and stick together. Okay. So there's no mentioning of any external resistive force acting on the system. So even if you just draw this surrounding box, you will find that there is no friction, there's no external force acting on the system. So as long as there is no external force acting on the system, the total momentum must be conserved. Now, if the total momentum is conserved, there must be no change in any sort of momentum. So any change in momentum is equal to 0, because there is no external force acting on the system, hence conservation of momentum is applied, and there will be no change in momentum because momentum is conserved. 0. Yeah, as a result of collision, the total momentum is still conserved because there is no external resistive force acting on the system. So there's no change in momentum because it is conserved. Question number 10. Energy is supplied at a constant rate. So it looks like the power supplied is constant because power is energy over time. To to a fixed mass of material. The material begins as a solid. The graph shows the variation of the temperature of the material with time. Okay, so we have time, temperature versus time. Call the time T and let the temperature be theta. Okay. The specific heat capacities of the solid, liquid, and gaseous form of the materials are Cs, Ci, Cl, and Cg, solid, liquid, and gas, respectively. What can be deduced about the values of specific heat capacities of solid, liquid, and gases? Okay, so we have to use this graph to find out which solid, liquid, or gas heat capacities are bigger and what is the correct order. Is it ascending or descending? Which one is the biggest and the smallest? Okay, let's see. So we will start from the specific heat capacity equation. So in the data bucket, we know that we are given Q equals to mc delta T. So delta T is a change in temperature. Here we will call it delta theta. Let me show you where this equation is. So if you, here, topic 3.1, Q equals to mc delta T. So delta T is a change in temperature. C is the specific heat capacity, Q is the thermal energy. So if you go back, in our case, we're not choosing delta T because we will get confused with this small t, which is the time. So we will just call delta T as delta theta. Okay, since we have to find small c, because everything is in terms of c, so just make c the subject. So c equals to q over m delta theta. Okay, so let's see, what does the slope of this graph represent? So the slope of this graph represents slope, rise over run. So the rise is in terms of delta theta, change in temperature, and the run is in terms of time, which is delta t. Also, you need to know that power equals to energy over time. This is the thermal energy form of energy. So this form of energy is the thermal energy. So you can make Q the subject. So if you make Q the subject, Q will be equal to P power multiplied by time. So just subbing this Q into here, and we will get power multiplied by time, which is just Q. And then we'll sub this equation into here, divided by m delta theta. This is C. Okay, so this is the slope of this graph. Now you can see this section of the equation. Isn't this the reciprocal of the slope? Because you can see slope is delta theta over delta t, but we have t over delta theta. Actually, you can just put delta t here because time always changes. Time doesn't stay constant. So in other words, we can actually rearrange the equation and write it as 1 divided by slope. Yeah, reciprocal, because we just need to invert it. So P is power. Power is constant because it says supplied at a constant rate. Mass is also constant. So if this part is constant, then we know that C is just inversely proportional to the slope. So the bigger the slope, the smaller the specific heat capacity. So let's see which one has the bigger or smaller slope. So this is solid, this is liquid, this is gas. So what can we deduce about the values of specific heat capacity? So let's give numbering. So the one maybe means the highest, and the 3 means the smallest or the lowest. Okay. So the highest specific heat capacity will be the one with the smallest slope, lowest slope, because they are inversely proportional. And the lowest slope is given to the gas. So the gas has, and then the second one is this, and then the third one is this, because you can see the liquid is the most steepest, the slope is the most steepest. So if the slope is the highest, according to the inverse proportionality relationship, the slope is the highest and the specific heat capacity will be the lowest. So the order is gas as the largest, and then we have solid, then we have liquid. So liquid is the lowest, or I should call maybe H, highest and lowest. So we will go from gas to solid to liquid. So gas, solid, liquid, part D. So an ideal gas of N molecules is maintained at a constant pressure P. The graph shows the volume V of the gas varies with absolute temperature T. So absolute temperature is actually calculated in Kelvin. So Kelvin is the SI unit for temperature, especially for ideal gases. So since we know there is an ideal gas, so the equation for an ideal gas is PV equals to nRT. Let's just copy down all the equations that we have from the data booklet. So if you go to subtopic 3.2 data booklet, so we will use PV equals to nRT. We will also use this mole equation. So moles equals to number of molecules divided by Avogadro constant. So let's also copy that equation here. So we have N equals to N divided by NA. And we will use one more equation, which is this last one. So average kinetic energy. Let's copy it here. Average kinetic energy is 3/2 Boltzmann constant times temperature equals to 3/2 R over NAT. So this R is a molar gas constant. So we have 3/2 R over NAT. So I'm just copying the equations from the data book. So let's just separate them. So all these equations are just taken from the data book. This is the average kinetic energies of the particles. Okay. So start from this equation. So ideal gas equation is PV equals to nRT. What does he want? He wants what is the gradient of the graph. So if you find the gradient of the graph, you always draw this triangle, then you say gradient equals to, so G for gradient is not gravity, yeah, it's a gradient. It's just you can choose whatever symbol you like. Gradient is equals to rise over run. So rise is due to delta V, changing volume, and the run is due to delta T, just changing temperature. So in other words, it's just V over T. So we have to derive and extract this V over T term from our ideal gas equation. So you can see there's a V here, there's a T here, so you can move this T down there. So V over T, and NR is still there, so you can also drag this P down there. So it's just simple mathematics. Just rearranging, cross-multiplying the equation. Okay, so V over T, so this V over T is the gradient. So this is equal to gradient, and gradient is, in other words, equals to nr over p. Do we have any option that says nr over p? No, there's no small n. So you can see there's no moles. It means he must have used this equation to get rid of this small. So we will substitute this n as capital N over Na. Let's do that. So this n is replaced by capital N over Na by using this equation. R is as it is, and capital P is as it is. Are we there yet? Still nowhere to be found. Okay, now we have to do some more work. Let's just rearrange the equation a little bit. So let's call it N over P R over Na. So I've done nothing but just rearranging the order. So I just move this N and P down there and Na. So just rearranging the order, no problem. But why did I do that? Because if you look at the third equation very carefully, you can see by simple comparison, 3/2 is equal to 3/2. T equals to T. As a result, this KB must be equal to this entire thing. So just by simply comparing the two equations, we have derived that KB, which is a Boltzmann constant, is equals to R over Na. Yeah, just compare the two equations. There's a 3/2 on the left, and there's a 2/2 on the right also. So compare left terms with the right terms. So left, right, left, right. So in that case, KB is equals to R over Na. So this equation is true. So what we can do is we can replace this entire R over Na by what we just derived. That R over Na is just equivalent to KB. So just simplify this equation more. So just rewrite it. So it will be N KB over P. So do we have the result? Yeah, it's C part. N KB over P. The pressure of a fixed mass of an ideal gas in a container is decreased at a constant temperature. For the molecules of the gas, they will be decreasing the mean square speed. No, the mean square speed will only decrease if the temperature decreases, because the speed depends on kinetic energy and the kinetic energy depends on temperature. So if the temperature doesn't change, then it means there will be no change in the mean square speed. So A is wrong. The number of striking the number striking the container walls every second. Yes, because pressure of a gas is always due to the frequency of the colliding particles against the wall. So when the gas particles collides with the wall of the container, that is what gas pressure actually means. So gas pressure is due to the amount or the frequency of the gas particles colliding against the wall of the container. So definitely this frequency at which the number of striking the container walls every second, it will decrease. Yes, this will decrease because the pressure has dropped, so it's going to be B. So you can just ignore C and D. Diameter, it doesn't change, and the magnitude of the force also doesn't change, so it has to be B. Okay. A body undergoes one oscillation of superharmonic motion, SHM. What is the correct direction of the acceleration of the body and the direction of its velocity? What is correct for the direction of the acceleration of the body and direction of its velocity? So imagine this is the ground, and you have a ball here, you have a ball here, you have a ball here in this ball. So call this as equilibrium mean position, and then probably we start from here and then goes there, come back. So it's performing superharmonic motion, and then come back to there. So this is one oscillation. Okay. So in this one oscillation, what's going to happen is, so the definition for superharmonic motion is that the acceleration is directly proportional to the displacement from the mean position, but opposite in direction. So the displacement and acceleration are always opposite in direction and directly proportional. Okay, so as the displacement increases, right? So if the displacement is in the forward direction, your velocity is also in the forward direction because you're moving forward. But the acceleration is opposing the displacement. So acceleration will be in the opposite direction. Now when the body is, for example, moving, maybe when the body is moving toward the equilibrium mean position, at that time the displacement is still in the forward direction, and then the velocity is, so this is displacement, this is velocity. If this is a velocity, then acceleration will be in the same direction. So acceleration will still be there. Yeah, because acceleration has to oppose displacement. So what is going to happen? So imagine it this way. So if the body is moving, let's choose a different color maybe. Yeah. So when the body is moving forward, your velocity is forward, but acceleration is in the opposite direction. Okay. So when the body is moving backward, your velocity is in that direction, yeah, and your acceleration is also in that direction. So they're the same. They're in the same direction. Yeah. And when the body is going in this direction, your velocity is in that direction, but your acceleration is in the opposite direction. When the body is returning, your velocity and acceleration are in the same direction. So you can see, for half of the time they're in the same direction, and for the rest of the half of the time they're in the opposite direction. So they will oppose each other for half a period. Period is the time taken to complete the cycle. So within the full cycle, half of the time, which time? When the body is moving toward the equilibrium position, both velocities and acceleration, they are in the same direction. But when the body is moving away from the equilibrium position, this is the equilibrium position, the acceleration and velocity will be in the opposite direction. So when they're moving away for half a period, they are opposing each other. And when the body is moving toward the equilibrium position for another half of the period, the acceleration and velocities are in the same direction. So they will oppose each other for half the time period. Time period is the time taken to complete one cycle. Question number 14. A particle oscillates with simple harmonic motion SHM of period t. So there's a time period t. Which graph shows the variation with time t with time of the kinetic energy of the particle? Okay, so first of all, you need to know that kinetic energy is half mv squared. I'll just change the color back to the red because it's a sharper color. Okay, now no matter what is the direction of the velocity, velocity is a vector quantity, so it has the direction, so it can either be positive direction or negative direction. But when you take the square of positive or negative value, it will always give you positive result. Mass is always positive, half is also positive, always positive. So positive times positive times positive will always give you positive kinetic energy. So kinetic energy is something that is always positive. There's no negative kinetic energy. So ignore any graph that has a negative part of it. So that has any negative kinetic energy, that is wrong. So you can see this graph is going down, negative, this graph is going down, below 0 is negative, so ignore these two. So it will be either V or D. Okay. Now in B of D, you can see the body is starting at the moment when the kinetic energy is maximum at the amplitude. So we're starting from here or here. Now if you draw the diagram of simple harmonic motion, for example, the body will be here, here, or here. Call this at equilibrium position. Okay, so if the body is supposed to be starting at a maximum kinetic energy, it means it must start from the equilibrium mean position because the velocity is always maximum at the equilibrium mean position. The higher the velocity, the higher the kinetic energy. So start from here, the body decelerates till it reaches the amplitude where the velocity drops down to 0, because that is the time when the body has to reverse its direction, but before reversing its direction it has to stop and then reverse. So at the amplitude the velocity decreases to 0, hence the kinetic energy also becomes 0 here. And then it returns, then it starts to accelerate until it reaches again maximum velocity, so the velocity becomes maximum here again, because the entire elastic potential energy stored is converted back into kinetic energy. And then it decelerates back to 0 velocity, and then it accelerates back to maximum velocity, so V max. So you can see in this one complete time period, how many times does the velocity get 0? 2 times. So one time is here, one time here, because there are 2 amplitudes. At both corner of the amplitude, the velocity drops down to 0. So it has to be 2 moments. There must be 2 moments where the velocity drops to 0. Not 1 moment, but 2 moments in one complete time period. So it has to be part D. Question number 15. A light ray is incident on an air-diamond boundary. Okay. The refractive index, so the refractive index is normally given by the symbol N, of a diamond is greater than 1. Okay, so the refractive index is bigger than 1. Which diagram shows the correct path of the light ray? So let's talk about what is refractive index. So if we open the diagram booklet and scroll back to Snell's law, in subtopic 4.4, this is the refractive index formula. So the ratios of the two refractive index, N1 over N2, is equals to ratios of the sine of angles equals to ratios of the two velocities in two different medium. Okay, so this is the formula. Okay, now if the refractive index happens to be bigger than 1, what do you think will happen? Well, if the refractive index is bigger than 1, always remember one thing. There is a phenomenon called total internal reflection. So total internal reflection occurs whenever the refractive index is bigger than 1. Yeah, because the refractive index of diamond, in our case, it will be the refractive index of diamond with respect to the refractive index of air, which is equals to the velocities ratio. So you can see, if you follow this equation, it will be equals to the velocity of the light ray in air divided by velocity of the light ray in diamond. So if it's like bigger than 1, it means that the velocity of the light ray in air is bigger than the velocity of the light ray they are equal. No, sorry. No, sorry. If it's bigger than 1, it means this one has to be small. So just remember, whenever the refractive index is bigger than 1, total internal reflection happens. So total internal reflection happens, when it happens, it means that the incident ray, this is the incident ray no longer refracts into the different medium. So refraction means when the ray passes from one medium to another medium. They're different medium because they have different densities. And total internal reflection says that when the refractive index is bigger than 1, the incident ray, no longer refracts into a different medium, but instead it reflects back into the same medium. So if this is the angle of incident, and this is the angle of incident, and the angle of refraction is always from the normal. So keep that in mind. This is the normal, so the angle has to be always from the normal. So if this is the angle of incident, this angle of incident will be equal to angle of reflection. So they will be total internal reflection. For example, if you exceed this thing here and then they still here the refractive index is bigger than 1, so what's going to happen? Total internal reflection will happen. So this is a phenomenon which is quite widely used in fiber optic cables, where you use this total internal reflection concept to transmit light energy from one point to another point. Yeah. The total internal reflection happens whenever the refractive index is bigger than 1, and total internal reflection means that the ray no longer refracts into a different medium, but it reflects back into the same medium. So angle of incident will be equal to angle of reflection, and always take the angle from the normal. So part A. A spring XY lies on a frictionless table with the end Y free. So there's a free end. So you can see there's a crust here, so wave formation. A horizontal pulse travels along the spring from X to Y. What happens when the pulse reaches Y? Part A is the pulse will be reflected toward X and inverted. The pulse will be reflected toward X and not inverted. Okay, wait, we have to be, so the concept here is, so you have only two cases, right? So we have a fixed end wall and a free end. So this is a fixed end and this is a free end. Free end means the rope is not attached to anything. Now remember, when the wave is incident toward a fixed end, the reflected wave will be inverted. But when the wave is no longer attached to any fixed end, it's a free end. If it's a free end, then the wave will no longer be inverted. So it will just reflect back with the same crust. There will be no inversion. So the pulse will be reflected toward X. Yes, there will definitely be a reflection. And if this will be true if it was a fixed end. This one is true if it's a free end. So in the free end there will be no inversion. So the wave will not be inverted. So it has to be part C. So you know the checks, so you can see 16B5, yes. Yeah, only for free end the wave is no longer, the reflected wave is no longer inverted, but for fixed end the reflected wave is always inverted. Question number 17. A student stands the distance of L from the wall, so there's a wall here. And there's a student here. He claps, so he claps, then he produces some sound wave. And this sound wave gets here, then gets reflected back. Okay. So the distance is actually between the person and the wall is L. Immediately on hearing the reflection from the wall, she claps her hand again. Okay, so it's kind of a cyclic pattern, frequency. Cyclic pattern, time period, frequency. She continues to do this so that the successive claps and the sound of reflected claps coincide. So there's a coincidence, so they're coinciding. So each time the wave returns, she claps again. Each time she hears the wave returning, she claps again. So it's a complete cycle. So in other words, the point of having this Concite means one wave, and then immediately you have a second wave, and then immediately you have a third wave. So in other words, you can see it's kind of a stationary wave also. So the dotted one is a reflected wave, and the solid line one is an incident wave. So you have incident and you have reflected wave. So they're coinciding each other, forming a complete time period, complete wave. The frequency at which she claps her hand is f. What is the speed of the sound in air? Okay, so the speed of the sound in air is a constant. It must be a constant speed because as long as the sound is in the same medium, here the medium is air, the speed will not change. The speed of the sound is dependent on various other parameters, but medium, the density of the medium is one of the parameters. So as long as the wave doesn't enter water or solid, its speed should stay constant. And the formula for a constant speed is just speed equals to distance over time. In our case, the distance that the wave travels is L plus L because it has to return. So it covers L, L, 2L because the wave is being reflected back. Divided by, so when the wave travels forward and then it returns back, this completes one time period. So you can see from the solid line and the dotted line, the solid line goes forward and then immediately the dotted line returns backwards. So you have this one time period. In this one time period, the wave travels a distance of 2L. So instead of just small t, you will say it's capital T because capital T is a representation of time period. And you can just further rearrange this equation into something like this. This is also true, it's just 1 over t. Now realize that this 1 over t is equals to frequency because we know that frequency is 1 over time period. So this is the equation. Frequency equals to 1 over time period. So we finally have 2LF. Part D. Question number 18. A negative 5 microcoulomb charge and a positive 10 microcoulomb charge are fixed distance apart. Okay, so we have two charged particles, opposite signs, fixed distance apart. Where can the electric field be zero? So electric field. So I need to find the electric field strength. So the electric field strength is given by electrostatic force per unit charge. So the definition for electric field strength is it is the amount of electrostatic force acting on per unit positive test charge. So this charge has to be unit positive test charge. Unit positive test charge. So the idea is, for example, if you have a charge particle here and these are the radially outward electric field, if you want to measure the electric field strength at any point, you always need to introduce a small unit positive test charge and then measure how much is the force experienced by this small test charge and use this formula to find the electric field strength. So electric field strength is also a vector quantity, so it is also direction dependent. So let's start with position 1. So if you want to find the electric field strength acting at position 1, you should always place a small unit positive test charge and then figure out what are the electrostatic forces acting on this small unit positive test charge. So this positive repel each other, so there must be an electric field strength acting in the opposite direction due to this plus coulomb charge. Let's call it plus. And positive negative attract each other, so there must also be, this is a vector quantity, so there must also be an electric field strength acting at this position due to this negative charge, because this negative charge is attracting the unit test charge, whereas this positive charge is repelling it. So call it electric field strength due to this negative charge, and it's also direction dependent. Now, what is the reason why did I draw this electric field strength a little bit smaller? So the length of the electric field strength is a representation of its magnitude. But the reason why I draw it smaller than this one is because this negative 5 microcoulomb is further away from this charge. Now, the further away the charge gets, the strength of the electric field will decrease. So that is why this electric field strength due to negative 5 microcoulomb charge has to be smaller than this one. So do you think they can cancel out each other? No. This one is a little bit longer than this one, so the overall there's a net electric field strength acting in that direction, because in the left direction there's more electric field strength acting, so it can never be 0. So ignore position 1, ignore any option that says position 1. So this one also has position 1, so we're only left with position B and C, option B and C to decide. Alright, let's just test position 3. If it doesn't work out, then it has to be position 2. Okay, let's measure the electric field strength, the net electric field strength at position 3. So to do that, we always introduce a small unit positive test charge, and then we find out what are the electric field strength acting on it. So the electric field strength acting on it due to negative 5 microcoulomb will be negative, positive attract each other, so it will be like this. So this is the electric field strength due to this negative charge. Is there any other charge? Yes, there is a positive microcoulomb charge. So positive repel each other. Now, what is the reason that I draw these two approximately the same size? So even though this plus 10 microcoulomb charge is stronger because it's double the charge, it's stronger, but it's also further away. So any increase in the magnitude of the charge has been compensated by being further away from the test charge. So there's a possibility that these two forces or these two electric field strength become equal but opposite in direction. And as a result, there's a very high chance that they will just cancel out each other, giving us 0 net electric field strength. So the electric field strength has a very high chance of being 0 at this position, because this is a position where the two electric field strength can become equal and opposite in direction. And why do they become equal? Because even though this is a big charge, but this one is also further away, so the distance compensates with the magnitude. So the electric field strength can drop to become equally at the same size for this one. So they can just cancel out each other, and it's very likely that the electric field strength will be 0 at this position. Yeah. Just 18 part C. Question number 19 is about Kirchhoff's laws. So there are two Kirchhoff laws, Kirchhoff current law and Kirchhoff voltage law. An electrical circuit is shown with loop X and loop Y. Okay, what is the correct expression for the Kirchhoff current law for loop X and junction Y? Let's see, where is junction Y? So there's a junction Y. So Kirchhoff current law always applies at a junction, and Kirchhoff current law that is applied at a junction says that the total current going in, so the sum of all the current going into the junction has to be equal to sum of all the current going out of the junction. So it is based upon conservation of charges, that charges can never be created or destroyed. So the total current that goes into a junction has to be equal to total current coming out of the junction. So what are the currents going into the junction Y? So there's I1 going in, so it has to be I1. Anything else that goes in? No. There's a current going out. There's a current going out here, I3. So I1 is going in equals to current sum of the currents going out. So there are two currents going out from the junction, and those are I2 plus I3. So this is one of the equations. I1 equals to I2 plus I3. So it's either this one and this one. So we can ignore B and D. So it's either A or C. Alright, this is Kirchhoff current law. This is always applied at the junction. Now, secondly, we have to apply Kirchhoff voltage law at the loop. So at the loop, we always apply Kirchhoff voltage law. Okay, so before applying Kirchhoff voltage law, we need to know the equation. So Kirchhoff voltage law says that the sum of the voltages along the loop has to be equal to 0. So Kirchhoff voltage law is based upon conservation of energy, and the energy is actually determined by the voltage. So voltage is actually a, a quantity, physical quantity that stores electrical potential energy. Voltage is energy per unit charge. Okay. Now it is based upon conservation of energy, that energy can never be created or destroyed. Okay. So before we apply or use this equation, we need to make sure that we assign correct terminal signs. We have to assign correct terminal signs to each component along this loop. So if you follow the loop, if you look at the cell, so this cell has a positive terminal. This is a positive terminal. This is a longer one, and the shorter one is a negative terminal. If you look at this resistor, the current is passing through the resistor in this direction. It means this side has to be more positive than this side. That is the only reason why the current is flowing in this direction, because the current always flows from higher potential, more positive, to low potential, less positive. Then the current goes here, 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 here to resistor R3. So this side has to be positive, this side has to be negative. That is the reason why the current is going from right to left, high potential, more positive, to low potential, less positive. And then the current goes all the way back to here. Okay, so no need to consider R2 because R2 is not part of this loop. We only consider the parameter, boundary of this loop. Okay, now let's add up all the voltages. So also remember that resistor equals to voltage over current. This is the equation. So if you make voltage the subject, I can go up there, so it becomes IR. So this is our equation, right? So what will be the voltage across this resistor? It will be its current and its resistor. Just multiply them together. So it will be I1 R1, and what will be the voltage across R3 resistor? It will be I3 R3. So we have this voltage here, we have this voltage here, and we have this voltage or EMF here. So we have three components to decide how to add them together. Okay, so let's start adding them together. So if you follow the loop, if you follow this loop, you can see this loop already has a direction. It's like clockwise. So the arrow of this loop. So let's pick one component. Where do you want to start? Do you want to start from this E or R1 or R3? Doesn't matter. Let's just start from E. So the arrow of the loop touches the positive terminal of E component. So it has to be plus E, right? Plus. Now the arrow of the loop touches the positive terminal of R1 first. So it has to be positive I1 R1. And then you follow the loop, and then here you can see still the arrow of the loop touches the positive terminal of R3 first. So it has to be positive I3 R3. Anything else? No. These are the only three components, so the sum of all the voltages has to be equal to 0. Let me give you an example. For example, if this was something like this, for example, if the current is like I1 and R1, and you can see if the current is going from right to left, this is positive part, this is negative, because the current always goes from positive to negative. And for instance, just for understanding, what if the loop was in this direction, opposite? In that case, since the loop arrow, the arrow of the loop touches the negative terminal of the resistor first, the voltage that is to be added must be negative I1 R1. So this is just for your understanding purposes. Okay. So in this time, the arrow of the loop is touching the positive sides of the terminal first, so we are just using all the positive voltages. So I think we need to make E the subject, so just make E the subject, and yeah, why don't we move this E to that side? I think it's much better. It becomes negative I1 R1 plus I3 R3. Yep, I1 R1 plus I3 R1. This just has to be A part. Yeah. Just rearranging, just bring the E along the other side of the equation and change the sign. So it has to be A part. A cell of EMF 4 volt and residual thinner resistance is connected to 3 resistors as shown. 2 resistors of resistance 2 ohm are connected in parallel and are in series with a resistor of resistance 1 ohm. Okay. So there is a 1 ohm resistor, there is 2 ohm resistors connected in parallel, there is no internal resistance due to the battery. What power is dissipated in one of the 2 ohm resistor and the whole circuit? So there are 3 different equations for the power that we can use here. So you know that power equals to IV also equals to I squared R and also equals to V squared over R. So for electricity purposes you can use any 3 of the equations, but I would suggest here not to use these 2 equations because they both have current information in it and we are lagging the current information. We can somehow use some equations to find the current first, but it will be more work, so we will avoid using these 2 equations. So we will avoid using this, and we will use the equation that does not have any information about the current. Because you can see we have voltage information, we have resistance information, so we have V and R. We don't have any current information. We can find current, but let's just avoid it so that we can solve it very quickly, more efficiently. So we will use power equals to V squared over R. Okay. Now he wants us to find what is the power dissipated in one of the 2 ohm resistors. Let's find out what is the voltage across these 2 parallel resistors. Okay, so 2 and the 2 ohm, when these 2 resistors are connected in parallel, the overall resistance will be half of it, which is 1 ohm. So just an example, if you have 3 resistors, if you have like 3 resistors and all of them are, for example, maybe 3 ohm, 3 ohm, and 3 ohm, all of them are 3 ohm. If you have 3 resistors connected in parallel and all of them are 3 ohm, then the overall resistance will be 3 divided by 3. So you have to divide by 3. So it will be equivalent to 1 ohm resistance. So if you have like 10 of them, then you just have to divide each resistor by 10. So it will be 3 divided by 10. So like that. Okay? So here we have 2 ohm resistors, 2 of them connected in parallel. We just divide by 2, and the overall resistance is 1 ohm. So now we have 1 ohm and 1 ohm, both of them are connected in series. This time the EMF of the battery will be divided along 1 ohm and 1 ohm equally. Why equally? Because both of them share the same voltage because they have same resistance. So this 2 ohm will be distributed equally among this and among this overall resistance, which is 1 ohm. So 4 is divided among 2 volt and 2 volt. Let's make sure it's correct. 2 volt plus 2 volt is 4. Yes. And each of the 2 ohm resistors share the same voltage because they are connected in parallel. And in parallel circuits, the voltage stays the same. Okay, so now we can use this equation. We can say, oh, the power dissipated across 2 ohm resistor is the voltage, which is 2 squared divided by how much is resistance? Also 2. So this is just 2 times 2 divided by 2. So 2 squared is just 2 times 2. Cancel out is just 2 watt. So power dissipated in 2 ohm resistor is 2, so it's either this or this. So ignore B and C. Let's find out what is the power dissipated in the whole circuit. So to determine power dissipated, we first need to find what is the overall resistance of this whole circuit. We already know that the resistance of these 2 combined is 1 ohm. 1 ohm plus 1 ohm gives us 2 ohm. So the overall resistance is 2 ohm. Why? Because 1 ohm and 1 ohm, they are both in series. In series we add up the resistance, whereas in parallel we divide, or we use this fraction formula, which is this 1 over R1, 1 over R total equals to 1 over R1 plus 1 over R2. So we use these fractional formula if the resistors are not the same. But if the resistors connected in parallel are the same, we can just divide by the number of resistors available in parallel circuits. So 2 and 2 in parallel gives us 1 ohm, and then 1 and 1 in series gives us 1 plus 1, 2 ohm. So the overall resistor is 2. So we can again use this equation. Overall, so what is the voltage provided to the whole circuit? 4 volt. So we will use 4 squared divided by overall resistance is 2. So this is 16 divided by 2, which is 8 watt. So it has to be deeper. wire carrying a current I is at right angle, so we have 90 degree. Now the reason why he's telling us is 90 degree because we will be using this sine of 90 and sine of 90 is just 1. To a uniform magnetic field of strength B. A magnetic force F is exerted on the wire. Which force acts when the same wire is placed at a right angle to a uniform magnetic field of strength 2B with a current of 1 volt? Same wire means it has the same length. So let me show you which equation we're going to use here. So if we just go down to topic 5, we will be using this equation. So the magnetic force is equals to BIL sine theta. B is the magnetic field strength, I is the current passing through the wire, L is the length of the wire inside the magnetic field, the length of the wire exposed to the magnetic field, and sine theta. Theta is the angle between the magnetic field lines and the length of the wire. It's the angle between the magnetic field and the wire. In our case, it's 90 degree, and sine of 90 is just 1. So let's use this equation. So F equals to BIL sine theta. Okay, so as you already know, the angle between the wire and the magnetic field is 90 degree, and sine of 90 is just 1, so we can ignore this sine part. So the overall simplified equation just becomes BIL. Okay, now we need to find the new force, call it F2, in terms of original F. So the new force is equals to new magnetic field, and the new magnetic field is 2B. So just replace this B by 2B. How much is the current? So the current has also changed. So our new current is quarter of the original current, and the length of the wire stays the same because we're using the same wire. It's the same wire that we are using. Okay. Let's rearrange the equation a little bit. So 2, 1, 2, 2. So this becomes 1 over 2 B BIL. Now realize that this BIL is equal to this F, because F is equal to BIL. So you can replace this BIL by this F. So our new force, the new magnetic force acting on the wire, is half the original force. So it has to be B. Yeah. Okay. An object at the end of a wooden rod rotates in a vertical circle at a constant angular velocity. Okay, what is correct about the tension in the rod? So there's a circular motion happening. So imagine this is the center, and this is the ball, and this ball is like undergoing a circular motion. Okay, just like for example, maybe moving in this direction, it has some mass. So at some point it is here, at some point it's here, and at some point it is right at the bottom. Okay, so we need to figure out about tension in the rod. Always remember one thing. So when the ball is right at the bottom, now even though it doesn't matter where the ball is, it's always undergoing superharmonic motion. It's always undergoing circular motion. So whenever a body is moving in a circular motion, there must always be a centripetal force acting on the body. And this centripetal force is a net, pure, resultant amount of force acting on it. And the centripetal force produces centripetal acceleration toward the center of the body. So there must be a centripetal force acting toward the center of the circle. So no matter where the ball is, centripetal force is always toward the center of the circular motion. So that is what we need to know. So centripetal force is always acting whenever there is a circular motion, and it is always directed toward the center of the circle. So when the ball is right at the bottom position, right? So at the bottom position, the weight is acting in the opposite direction. right? The weight always acts downward toward the Earth, but centripetal force is required to be in the upward direction. So it is the tension in the rod that must be responsible to provide enough force so that not only can it counteract or balance out the weight, but also provide additional centripetal force to make sure it stays the net. Yeah. So when the rod is exactly at the bottom position, the tension must be maximum because the tension is responsible to provide not only the weight. The tension has to not only overcome the weight but also provide additional net centripetal force in the upward direction so that this weight is cancelled out and the remaining force provided by the tension is equal to centripetal force. In other words, you can say tension at the bottom position is equals to weight plus the centripetal force. So yeah, it's the centripetal force and both of them are acting in the upward direction. So the tension has to be greatest at the bottom of the circle. Vice versa, the tension in the rod is smallest when the rod is at the top position because the centripetal force is still downward toward the center of the circle. The weight is also downward, so the weight helps the tension to provide most of the centripetal force. So the tension doesn't need to be too much because the weight is in the direction, downward direction, that favors the centripetal force. So the tension doesn't need to provide a lot of force because it's no longer overcoming the weight, but instead the weight is supporting the tension to provide the centripetal force, which is net and acting toward the center of the circle. But when the rod is at the bottom position, the weight is counteracting, it is opposing the centripetal force. So the tension should not only overcome the weight, but also provides that additional centripetal force. So it's greatest at the bottom and minimum at the top. Question number 23. On Mars, the gravitational field strength is about 1/4 of that on Earth. Okay, so we can write it down mathematically. The gravitational field strength on Mars is 1/4 of gravitational field strength on the Earth. So G on the Earth, G on the Mars. So subscript M is for Mars, E is for Earth. Okay. The mass of the Earth, so call it mass of the Earth, M subscript E, is approximately 10 times that of the Mars. So it's approximately is like equal sign, 10 times that of the Mars. So M for Mars. So E and M are the small m and small e are the subscript. So the mass of the Earth is 10 times the mass of the Earth. So this information is given to us, so when we represent it mathematically. What is the ratio of the two radiuses? Okay. Now we will use the first equation. We will say the gravitational field strength of the Mars is 1/4 of gravitational field strength of the Earth. Okay. Now if we go back to our data booklet, we can see that the formula for gravitational field strength is Gm over r squared. This one. So we can write it down there. So gravitational field strength, which is a vector quantity, is Gm over r squared. Let's sub it here. So it's going to be Gm over r squared equals to 1/4 Gm over r squared. Now this side is for the Mars, so it has to be for the Mars, and this side of gravitational field strength is for the Earth. So it has to be mass of the Earth and distance from the center of the Earth, or you can say radius of the Earth, because we are saying on the surface. On Mars means, and on Earth means on the surface. So this is a planet. So if you are measuring gravitational field strength at this point, you're actually measuring it at the distance of r, which is equivalent to the radius of that planet. So r just becomes the radius of the planet because we are measuring the gravitational field strength at the surface. So we are radius distance away from the center of the planet. Alright, now we just need to rearrange the equation. So we need to make sure that the radius of the Earth is on the top in the numerator. So we can just move this RE over there. Actually, this G and G just cancel out, and RE can go to that side. RE over RM, and you can see both of them have a square, so why not we just take square common out. P equals to 1 4 ME over MM. So this MM can go down there, just cross multiplication. Okay, now let's rearrange it a little bit. So we have M of M, but you can see M of E, this M of E can be replaced by 10 of M of M, 10 times the mass of the Mars. Whereas this M and this M cancels out, so we have 10 over 4. So this is equals to 10 divided by 4. So you can see we have this square. So in order to get rid of this square, we have to take square root on both sides. So this cancels out. So we have radius of the Earth versus radius of the Mars is equals to, what is square root of 10? Yeah, this is a tricky one. So actually this thing can be written as square root of 10 divided by square root of 4 using simple indices rules. So let's keep this one as it is, and square root of 4 is 2. Okay. Square root of 10, so think of a number, for example, 3 square root is 9. So it means 9 is closest to 10. So square root of 10 will be just a number just bigger than 3. So maybe 3 point something. Let's just approximate it to 3. If 3 square is 9, then square root of 10 will be 3.1, something like that. So 3 divided by 2, which is approximately 1.5. So any number that is closest to 1.5, yeah. Part C is 1.6, and 1.6 is closest to 1.5. Okay. Photons of energy 2.3 electron volt are incident on low pressure vapor. The energy level of the atom in the vapor are shown. Okay, so these are the energy levels. So probably the nucleus is somewhere here, and the nucleus has protons and neutrons, because as you move away from the nucleus, the energies of the energy level shell should decrease. It should increase, yes, it becomes more and more positive. So as you move the electron away from the nucleus, it becomes more and more harder to move it, because you have to provide more and more energy. So the energy level increases as you move away from the nucleus. So the nucleus is overall positively charged. Okay. So as you know, photons are energy particles of the wave, and photons are discrete in nature. So they occur in a fixed amount. So they are incident. It means, so there is a light that contains photons, and the energy available is 2.3 electron volt. So this is a discrete amount of energy. So if there is any electron in any one of the shell, the electron can only be excited to a next higher energy level shell, such that the exact difference between the two energy level shell is equivalent to 2.3 electron volt. Yeah, because the energies are discrete, so they have to be exactly equal in order to absorb and then get excited and jump up to the next energy level shell. So we just need to find the difference between the two shells, whose difference is exactly equal to 2.3 electron volt. Now, for example, if you have an electron at a lower energy level shell, negative 3.9, so this negative 3.9, so if you look at the option, for example, option A, so if the electron is at negative 3.9 electron volt, can it jump to negative 1.6? It will, if the difference between these two shells is exactly equals to the incoming photon energy. Let's see. So we are at negative 1.6, higher energy level shell minus lower energy level shell, and the lower energy level shell is at negative 10. So if you solve it, you will get 2.3 electron. Well, yes, perfect. So the energy level difference between this shell and this shell is exactly 2.3 electron volts. So yes, this transition of of jumping of an excitation is feasible. Yeah, so an electron that is sitting at a lower energy level shell can absorb this fixed amount of energy and jump to the next 1.6 electron volt shell. So it has to be 8 pi. So this transition is possible. Now remember, never jump down, because jumping down means energy is released. So it's an emission case. But now we have an absorption case in which energy is being absorbed, and as a result, the lower energy level electron are able to jump to a higher energy level shell, provided that the energy level difference is exactly equals to the amount of energy, discrete amount of energy supplied. So when alpha particle has 4 nucleons, 2 protons. So nucleons consist of both protons and neutrons. Collides with the nucleus of nitrogen 40, so we have nitrogen, 14 nucleons and 7 protons. So for this nitrogen we have 7 protons, and how many neutrons do we have? Just subtract the 2. 14 minus 7, 7. So we have equal number of protons and neutrons. Okay. Collides with an alpha particle, so it collides with alpha. Alpha has 4 and a 2. So let's see what is the alpha composition. So alpha has 2 protons and also 2 neutrons. Okay. So what's the result? A nucleus X is produced. So nucleus X can be produced together with a proton. So plus a proton. So if you use conservation of charges, you can see totally we have 7 plus 2, 9 protons. So 9 minus 1, we will be left with 8 protons. So you have the number of protons and neutrons on both sides must be conserved. So on the left hand side, in the reactant, we have 7 plus 2, 9 protons. On the right, we should also have 9 protons. So because one of the proton is lost, so there are 8 left. So it has to be the one with 8 protons, is either A or B, so ignore C and D. What about the nucleons? The nucleons number must also be conserved, so we have 7 plus 2, 9, and 9 neutrons, so we should also have 9 neutrons there. How many protons do we have? 8. So just add them together. So 9 plus 8 is 17, so we have total 17 nucleons together. So nucleons are the sum of neutrons and protons. So this is the chemical composition with this element X, 17 and 8. Okay. Conservation of charges. Both protons and neutron numbers are conserved. 26. The mass defect for deuterium is this much. What is the binding energy of deuterium? So binding energy is actually given by this formula. So the binding E equals to mc squared is the equation. So this E is the binding energy, and this m is the mass defect. So normally we write this equation in this form. So this is the binding energy released or gained equals to mass defect times square of the speed of light. So c is the speed of light. Okay. But this result gives us energy in terms of joule. But we are dealing with energies in electron volt. So in order to convert an energy, which is in joule, to equivalent energy in electron volt. Electron volt and joules, they are both a unit for energy, but joules is SI unit for energy. So in order to go from joules to electron volt, you need to divide by the charge of electron, and the charge of electron is 1.6 times 10 to the power negative 19 coulomb. Yeah, and vice versa. If you want to go back, you need to multiply by the charge of electron. This is called elementary charge. It's also given in the data. Negative 19. Okay, so we want the result to be in electron volt. So in order to go from, so this will give us answer in joule. To go from joules to electron volt, we have to divide by the charge of electron. Call it E for now. We just plug in all the numbers. So the mass defect is given to us, which is 4 times 10 to the power negative 30 times the square of the speed of light, which is speed of light is 3 times 10 to the power of 8. Take the square, divide by E. E is elementary charge, which is 1.6 times 10 to the power negative 19 coulomb. Let's solve it. Okay. So we have 4 times 10 to the power negative 30. So if you look at this part carefully, 3 square is 9. So we have 9 here. Okay. And 8 times 2. So don't take 8 square. It's 8 times 2, which is 16. We have to add up 16 here in this rule. And then if you look at the denominator, we have 10 to the power negative 19. When negative 19 goes up, it becomes... Okay, instead of moving negative 19 up, why don't we do like this? Actually, let's just move negative 19. Yeah. So negative 19, when it goes upward, becomes positive 19. So on the bottom, we are only left with 1.6. Let's simplify this thing a little bit. So we have 9 times 4, which is 36, divided by 1.6 times 10 to the power of negative 13 plus 16 plus 19. So negative 30 plus 16 is 10, 14 plus 19 is 14 and 19, we are going to add them together. 33. Okay. This is 33. Okay. Negative 13 plus 16 plus 9 is actually 5. This is 5. Yeah, just do simple mathematics. Negative 13 plus 16. Negative 14. Negative 14 plus 19 is 5. Okay. And we can also multiply both sides by 10 so that we can get rid of this decimal places. So we have 36 divided by 16 times 10 to the power of 6. Now this is going to be 2 times 10 to the power of 6. Yeah, so 2 times 10 to the power of 6 is the answer. Okay, good. Okay, so as quarks separate from each other within a hadron, the interaction between them becomes larger. This is a topic on nuclear physics. What is the nature of this interaction? So, interaction with hadrons. Is it electrostatic, gravitational? Definitely not gravitational, because gravitation is always there, and it's always between masses. Whenever there's a mass, there's always gravitational, and that gravitational is always negligible. Electrostatic? No, because electrostatic exists between charged particles. So electrostatic is between charged particles. It is appreciable, but it's only between charged particles, and we don't have any charges there. Gravitational is always there between masses, but it is almost negligible because it's very small. So it's either C or D, and since hadrons are involved, it has to be C. So if you want to learn more about these hadrons, so let's just read this paragraph. Hadrons that interact by the strong interaction are called hadrons. This general classification includes mesons and baryons, but specifically excludes leptons, which do not interact by the strong force. The weak interaction acts on both hadrons and leptons, but we are not dealing with leptons, we are dealing with quarks. Okay? Hadrons are viewed as being composed of quarks, either as quark, antiquarks, or mesons. So here is your answer actually. So particles that interact by the strong interactions are called hadrons. So we choose the option that says strong interaction. Strong nuclear forces exist between hadrons and electrons. Question number 28, Sankey diagram. So a Sankey diagram represents the energy flow of coal-powered power station. Coal-fired power station, okay. What is the overall efficiency of the power station? So the efficiency is overall output over input. So output over, actually we should say useful output. Useful output over total input. Okay, So what is the useful output? Let's see. So energy to the consumer is the useful output. Let's count the number of boxes. 1, 2, 3. So we have 3. Anything else is being useful output. Energy used in transmission known as wasted. Energy used in power stations wasted. Thermal energy losses in power station also wasted. So the useful output energy is the energy supplied to the customer, which is called quantitatively is 3 boxes, and the total energy input is how many boxes? So it's like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So it's 10 boxes. So 10 divided by 3 divided by 10 is 0.3. So the efficiency is 0.3. So efficiency is the useful output work divided by total input energy supply. Yeah. Which of the following is not a primary energy source? Wind turbine is a primary energy source because it can provide energy to a large residential area. Coal-fired power station is also can provide energy to large residential areas, and so as nuclear power station, but jet engine is only used to power up jet engine only, and it only lasts for a short period of time, maybe a flight of 8 hours, so it can only last as long as there is fuel, and the fuel will burn out within 8 hours of flight time period. So jet engines do not provide primary energy source, but they only provide energy source to that short period of time during the flight. It can only be used for like one plane. It does not provide energy to a large residential areas as compared to these three. So this is the answer. So jet engine do not provide primary energy source. What are the principal energy changes in a photovoltaic cell? So photovoltaic cell are the cells that are using solar panels and solar heating panels. So both of them are renewable source. Both of them use renewable source of energy. So what are the principal energy changes in photovoltaic cell and solar heating panel? So in photovoltaic cells, so you can see voltaic, so it has to deal with electricity. So it converts photo means light energy and voltaic means electrical energy. So we are converting solar into electrical. So it's either this or this. And solar also light and heat mean thermal. So we are converting solar to thermal energy. So solar to thermal. So it has to be A. Alright, we are finished. Thank you very much.